Today we're starting our last unit of the year. It's called Simple Harmonic Motion and Waves. Now, in some respects, those two parts of the unit, the simple harmonic motion part of it and the waves part of it, seem to be distinct from one another. There's going to be this transition from simple harmonic motion to waves that in some ways is going to seem like, what do these have to do with each other? But in other ways, they're closely related. They're intertwined with each other. So we'll talk about that a little bit more as we get to that point where we split between simple harmonic motion and waves. Let me define simple harmonic motion first of all, and then as I say, in another week or so, we'll tie it into waves. Simple harmonic motion is motion in which something we call restoring force is proportional to a displacement. What do I mean by that? What do I mean by that? Well, if I pull an elastic, the further I pull it, the bigger the value of x, the bigger the displacement is, the more force it pulls back with. So in other words, that's simple harmonic motion. It's motion in which the force pulling it back to where it came from gets bigger as it gets further away from its natural position. Spring and elastic, both good examples of simple harmonic motion where the more it's stretched or the more it's compressed, the bigger the force that it pulls back with. Motion in which the restoring force is proportional to the displacement. Now, what's the implication of the restoring force being related to the displacement or proportional to the displacement? Usually that results in motion that repeats itself. So if you take a spring and you pull it back, the restoring force that pulls it back towards its natural position gets bigger. The further away you pull it from its natural position, the bigger the displacement. But if you let that spring go, what happens to it? It vibrates back and forth and back and forth and back and forth. Same thing with an elastic. Although the vibration dies out fairly quickly, for a short time, it's vibrating back and forth, back and forth, back and forth. Even something like this. I take the meter stick and hang it off the edge of the desk, and I do this. Okay, the more I push down on it, the harder it is to push down. That means the harder it's pushing back. Its natural position is straight. The more the displacement, the more the force that pulls it back towards its natural position. Now watch what the implications of that are. I push it down and let it go. It vibrates back and forth, back and forth, back and forth. So the restoring force is related to the displacement. That's the real definition. But what does it really mean? Motion that repeats itself. So examples, as we said, a vibrating spring. I'll write down, although this isn't a particularly common example, I'll write down the vibrating meter stick as well, only because you might, when you're reading your notes, remember that. Remember what we just did in class here. What's another example of simple harmonic motion? Motion that repeats itself, motion in which the restoring force is proportional to the displacement. This is the last thing that we need to do so that you can complete your field trip assignment that we're going to do next week. A pendulum. You guys know what a pendulum is? If I take these keys on the end of this string and I pull it back here, the more I pull it, the more it pulls back to its natural position. So the restoring force is proportional to the displacement. Now what happens when I pull it back and let it go? It repeats itself. It's a motion that repeats itself. So a pendulum is a pretty good example of simple harmonic motion as well. It's a little bit of an approximation, to be honest. It's not perfect simple harmonic motion because the restoring force is not perfectly proportional to the displacement, but it's real close. So we usually say that it is simple harmonic motion. Now, we're going to define a term that we've already defined. That's always good because we know it. Frequency. We defined it in our last unit. Circular motion is the number of vibrations or the number of cycles in a certain amount of time. The number of vibrations, the number of cycles per second. And we can find the frequency of an object going in a circle by calculating the number of revolutions over the total time. When we're talking about simple harmonic motion, it's not revolutions that's a cycle, it's one complete back and forth motion that's the cycle. So we're going to say it's the number of cycles divided by the time, just like it was in our last unit. The period is the time for one cycle, same as it was in the last unit, except one cycle in the last unit was one complete revolution. In this unit, one cycle is one complete back and forth motion. Like this. Pendulum goes up like this. Okay, one complete cycle is now. Okay, back to where it started, right? Starts here, back to here. That's one complete cycle. The period, the time that it takes for one of those cycles is the period. Now we can find the period by saying the time over the number of cycles. And of course, we can tie those two together, frequency and period, by saying T is equal to, 1 over F. This one that's squared off is the one that appears on your data sheet. The other two are more just definitions, and that's why they didn't appear on your data sheet for the last unit or for this unit either. Got it? Yep.
What about one of those things where it's got like little marble balls on the thing, kind of like you use one up?
Yeah, Newton's Cradle it's called. Like this thing right here.
Yeah.
Yeah, that would be simple harmonic motion, but there's a little bit more going on there because there's a collision and some momentum and energy transfer going on there as well. But in the end, well, that wasn't simple harmonic motion. Yeah, it might work better.
Yeah.
This isn't a very good one either, so. That one doesn't want to stay in the middle there. Yeah, this one's kind of off. But in the end, it's still motion that's repeating itself, and it's motion in which the restoring force, okay, as I pull this up, the force that's pulling it back down to the bottom there is proportional to the displacement. The force becomes bigger as it gets further away from its natural position where it's at right now. Yep. All right, let's do one example and a couple problems to go with it, and then that's it for the day. Nice way to start off a new unit, right? 10 minutes of new stuff. What's the frequency of an automobile engine in which the pistons oscillate with a period of 0.0625 seconds? Boy, oh boy. Especially a good way to start off the unit. This is easy, right? Here's the period, 0.0625 seconds. We want to find the frequency. All we're going to do is say, well, we know T is equal to 1 over F. F is therefore equal to 1 over T. 1 over 0.0625 equals 16 hertz. We've done this question before, really, right? In the context of circular motion. Notice the slight difference, though. Okay, this question isn't involving an object going in a circle. We still do it the same way as we did in the last unit, but it's not literally going in a circle. It's going back and forth, back and forth, back and forth. All right, so your homework? Boy, this should take you about 45 seconds, I think, this homework for the weekend. Make sure it's done, please, for Monday.